classic story goes something like this. I was standing in awe of the Tyrannosaurus Rex skeleton when the security guard came over and says, "Did you know that this skeleton is 130 million and 5 years old? Oh, and don't forget the 6 months." And I respond, "Well, how did you know this?" And he says that when he started, they told him that the skeleton was 130 million years old. And that was 5 years, 6 months ago. Now, hopefully you can see the error in the security guard's way. So you can see from this story that the number of figures you give an answer to is significant and can also affect the answer you give. And this is why it is important to GCSE and A Level physics. So in this video, I want to discuss the following things. What is significant? How we decide how many are significant? How we go about using them? What is standard form and how do we use it? And then finally, some examples of writing different numbers to different numbers of significant figures and where they become important. Right, quick Wikipedia search comes up with the following. Significant figures are digits that carry meaningful contributions to a measurement. Meaningful. What do we mean by that? How do we decide what is meaningful? Okay, so what is significant? To start off, the simple rules are: number one, any non-zero digit can be significant. Leading zeros, for example, in this number, 0.000426, all the zeros are not significant, but the 426 is. So this number has got 3 significant figures. Number 3, trailing zeros. Most of the time, and we'll discuss later in this video more in depth, are generally not significant. So in the number 18 million, all those zeros are not significant, and this is only written to 2 significant figures. So 1.56 million is 3 significant figures, 49,000 is 2, and this final number, that is written to 4 significant figures. Deciding on the number of significant figures to use. So hopefully you now know what is significant and meaningful. But who decides how many you should use? Well, you should, depending on the situation you're in. Situation 1, making measurements. The resolution of your meter decides the number of significant figures you use. So if you use a ruler to make a measurement, it will measure generally to the nearest millimetre. So you can make measurements to a maximum of 3 significant figures. Using a micrometer or a vernier caliper, you could read as many more significant figures, maybe 4 or 5. This means there is no point though giving a further result to a greater significant figure than the initial measurement. If you say measure the area of a piece of paper with a ruler and calculate this area, you should only give it to 3 significant figures, as that's what your initial measurements were in. Okay, situation 2, errors in measurement. Any measurement you make will have some sort of error in them. But errors, that's a topic for a totally separate video because it'll take too long to discuss here. When it comes to errors, we generally are only estimating them, so 1 or 2 significant figures will be acceptable for them. Okay, situation 3, exam questions. Now these are the most common area, place, whatever, you will have to deal with answering to the correct number of significant figures. Now, generally here, we get this from the question. Depending on your level of physics, whether it's GCSE or A Level, for the WJC will depend on how many significant figures they will expect. For GCSE, generally they don't care as long as you round and you give it to a sensible number of significant figures, if you round correctly, sorry. But A Level, they do get a little bit more picky. Okay, so for A Level, they want you to look at the question and give your answer to the same number of significant figures as are in the question. You might get away with +1. You definitely won't get away with -1, but you might get away with +1. Okay, so how many significant figures are in the data in the question if we look at this question? Well, if you read through, I'd say 2. 16, definitely. 40 goes back to those trailing zero questions. Yeah, definitely 40 could be 2 significant figures, but most likely it was 1. So our answers here should always be given to 2 significant figures. You might get away with 3, possibly 3 in the early calculations, but our final answer should definitely be just 2. So if you want to work it out, the horizontal velocity here is 12.3 meters per second and the vertical is 10.3 meters per second. Using significant figures. So now we know what is significant and we now know roughly how many we should be using. But what about taking numbers which have way too many significant figures, or way too many figures, and reducing them to the significant figures that we need? Now, you should be used to rounding a number to a certain number of decimal places. However, if you're not, just a quick recap. Firstly, you count the number of places after our decimal point. Check that the next number is less than or more than 5. If it's less than 5, we leave it alone. If it's more than 5, we round up. So, for example, 0.3456. So 2 decimal places would be 0.35. In here, the 4 has been rounded up because the next number was 5, which is 5 or more, so we had to round it up. Well, the significant figures, the same applies. Count your significant figures, look at the next digit. If it's less than 5, leave it alone. If it's 5 or more, round up. After this, we replace all the final digits with zeros. Okay, so we've got 23,455,095. If we want to make that 3 significant figures, it's going to be 23.5 million. Where significant figures become tricky is with decimal places. Remember earlier where I said that leading zeros are not significant? If not, go back, watch that bit again. So it means that in this number, all the zeros are not important. Our first significant figure is the 4. Also earlier I said that trailing zeros are not significant most of the time. So when are they? Let's take a look at those examples. Okay, so if I have 23, 23.00 and 23.000 meters, which of these is measured to the nearest millimeter? How can you tell? Well, that's by the trailing zeros. We can imply the resolution of a measurement by how we write a number down. By adding trailing zeros after a decimal point, they become significant and they show the resolution of the measurement. So our 23.000 is the one that's measured to the nearest millimeter. 23.00 to the nearest centimetre, and 23 would imply that that's to the nearest metre. So what's standard form and how do we use it? Right, so far we've written a whole lot of nothing. And it's amazingly easy to lose track of nothing. So we need a way to simplify this. This is where standard form or scientific notation comes in. Standard form is all about the order of magnitude, or how many powers of 10 a number has within it. So for example, 2000 is 1,000 times, or 1 times 10 to the 3, or 3 orders of magnitude bigger than 2. Okay, using standard form then. So to correctly write 2.2 million, in standard form, we first write out a 2, then a decimal point, then another 2, as these are our only significant figures here. We count up all the zeros, adding on 1 for any other digits we've written after the decimal point. So in our case, we've got 5 zeros, plus 1 for the 2 after the decimal point, and that gives us a 6 for our powers of 10. So in our example, this is going to be 2.2 times 10 to the 6. What about tiny numbers then? Well, these are a bit trickier, but if we follow a similar pattern, we can write these down. So let's start off with this number here. First, we write down our first significant figure, which is 2. Then a decimal point. Then we write down any other figures that we've got that are not zeros. In our case, just a 4. Now what we do is we need to work out our powers of 10. So what we do here is we count our zeros. So we count the zeros, including the one before the decimal point, and this gives us our negative power of 10. It has moved the decimal point to the left, so these are negative powers of 10. And again, here is 6, so our number here is 2.4 times 10 to the minus 6. Now this is great, and scientists, especially physicists, play a little bit fast and loose with these rules. This is proper mathematical standard form. When it comes to using it in science, we change it slightly. We change it slightly because of prefixes, things like nano, kilo. And we will look at that in another video when we go through units. Okay then, in summary then. So, in summary, significant figures are the numbers that give meaning to a result. The number of significant figures we use depends on the resolution of a measurement, the numbers given in an exam question, or errors. Remember, we don't count leading zeros, and most of the time we don't count trailing zeros unless they are after a decimal point. Standard form makes writing large numbers with lots of zeros a lot easier by combining powers of 10. And the final piece of this video, a lot of the ideas that were in this video came after reading a book called Maths on the Back of an Envelope by Rob Easterway. I'll put a link in the description below. It's a fascinating introduction to the art of estimation and the way of checking are calculations correct, or doing, as says on the back of an envelope, rough calculations to make sure that what you've done is right, to make sure that you're not being ripped off, to make sure that when you hear of numbers in the news, do they make sense? I would really suggest, guys, I've said it before in a video, go read it, go listen to it if you've got Audible. There's some really powerful stuff in there that will make doing calculations an awful lot easier. And the last thing I'm going to say, thanks for watching. Give us a comment, see ways to improve, things you'd like to see in future videos.